Good afternoon. Let's get started. We had a snow day, so that means we have one day to review before the big midterm. So I'd like to dedicate pretty much the whole class today to review. Before we get right to the review, I have two quick demos, I guess you could say, of a couple things that we didn't get to last class. So I do want to show those off real quick, then we're going to get to the review. The first is, and you can see the video of it on this camera right here. The first is what you're looking at is an overhead shot of this trash can. This trash can has like a spandex, like a spandex cloth taped over it, and then there's the spandex is pulled down into the middle using a bolt. So that spandex is pulled down in the middle. So right here in the middle there's a bolt pulling it down. So you might be able to, I don't know if you can see it in that camera, but the profile is kind of this dip. So the profile, you can see it kind of dips down. So that's what you're seeing there. And the reason I have that there is late 1600s, Newton says, hey, there's this thing called gravity. The story goes an apple fell from the tree. Who knows? But Newton says there's this thing called gravity. About 300 and some years later, it took about 330 years, actually. It took about 330 years till someone came along and gave a really good explanation for what that is. And so Newton says there's this thing called gravity. It's GMM over R squared. I got a formula for it. I can describe it. I can use it to describe why apples fall from trees. I can use it to describe why planets go around the sun and moons go around planets. That's great. That was a huge accomplishment. Never really had any idea what it was. Really what it was. It took 330 years. Einstein comes along and says, here's what gravity is. You want to know why two things are attracted? Why an apple is attracted to the Earth? Why the Earth is attracted to the sun and the moon is attracted to the Earth? It's because anything massive makes a dent in space itself. That's what Einstein comes along and proposes just based on the math. He has really nothing leading in that direction other than the math. So here's what Einstein says. He says that what if, and this is completely bonkers to hypothesize this, that space itself, that thing that we think of as just the absence of other stuff, is a thing. So clear out all the people and all the chairs and all the air and the building, everything, you're left with a thing called space, and that thing can be manipulated, can be twisted, bent. And that's what you're seeing right there is a model of that. So what Einstein says is the reason two things are attracted to one another is because they're both responding to bent space. And in fact, according to Einstein's ideas, and we've since seen proof of this, light always, and we haven't talked about light in this class, but light always travels in a straight line. Sometimes you watch light do this, not travel in a straight line. The reason for that is light is traveling in a straight line in bent space. And that's actually, we've actually observed that. And so what you're looking at with this orange spandex cloth is a model of what maybe a planet would do. All of us bend space-time. According to Einstein, we think he's right. All of us bend space-time, but such a tiny amount. In order to bend it significantly, you have to be very, very, very large, something like a planet. So what you're looking at here is the amount of bent space that maybe a planet would create. And so if I take another object, and place it near that planet, it's going to be attracted. So next time you drop something, watch it fall to the Earth, one way to explain that, and maybe the correct way to explain that, is that what's happening is the object you dropped was just rolling down into a dent of space-time created by the planet Earth. So the planet Earth creates a dent like this. So put anything near it, and it's going to roll toward the center of the Earth. It's going to fall into that dent. And so Einstein actually tells us, gives an actual description of what is actually happening, why things are gravitationally attracted, and a good explanation, and like I said, we think he's right, is that there's dents, and things follow those dents. And in that one you just saw, sometimes, like if I just drop something, it's just going to fall straight down, and that's what I'm trying to demonstrate here, is just falling straight down. But sometimes if I get going fast enough, I might miss the Earth on my first pass, like a comet, and I might actually orbit. And so you can actually explain orbits by the same idea. So the reason that the moon is orbiting the Earth, the moon is actually going in a straight line, following a curve in space. And so the reason the moon is doing that is the moon is basically doing this. You can see that orbiting. So if the central dent in this demo, if the central dent is a planet, you can see how things like satellites and moons might orbit that planet, because really they're just following the contours of space, the dent created by the existence of the planet. And then the last thing that we found out just like a week ago is that if this mass were to change very rapidly, and I can't demonstrate that, but if this mass were to change very rapidly, or just even if there was a distortion that happened very quickly, you can imagine that I can create ripples. I can create ripples. So if I were to just maybe just do that, throw something off of it or something, just hit it like that, something. If I were to rapidly change the amount of mass right there, you could imagine that would create ripples, and those ripples would propagate out. And you can't really see it, but at a super slow-mo camera, you can see the boing, you can see the boing, right? You can see that happening. And so if I hit it really fast, you can see that. By me hitting it really fast, what I'm sort of representing is a rapid change in mass, a mass that was there and is not there, or vice versa. And that's what we think we detected when we detected those gravitational waves, that we had about 60 solar masses of stuff making a huge dent in space. They were black holes, so it's as big as a dent as you can make. The dent actually goes down to a point. And so two very, very massive things that all of a sudden merged and lost some of their mass, and there was this ripple that went out through space itself at the speed of light, also calculated by Einstein. So just using some 1916 math, he was able to figure out that there is a thing called space-time, how it might behave, how it might be bent, and what the result of something insane like two colliding black holes would be. And what we've observed matches that very, very closely. Okay. So that's just a quick demo about gravity, general relativity, gravity waves. The last class we were reviewing, I think it was last class, we were reviewing energy, and I ran out of time. Right at the end, I was showing you some ways to convert energy. So one of the big understandings of the last few classes, energy cannot be created or destroyed, energy is never destroyed, energy is never destroyed. However, it changes forms. It's transferred from one thing to another. And if I want to do anything in this universe, I need energy to do it. And so one of the examples I did right at the end of last class, I just wanted to repeat because I was in a hurry. Jeez. Let me change my camera here. Let's do that guy. So yeah, you can see the car there. So I just wanted to repeat it because we were short on time last class, is that I have a pretty complex system up here. Right now, we're paying the power company to convert some sort of potential energy into electric energy. So like I've said, Dominion, they produce a lot of their power with nuclear, so they're actually taking plutonium and they're converting some of that mass into energy, and that energy is then spins a big turbine, which spins a big magnet, which pushes electricity all the way to over here to UVA, and then I can use that. Or maybe maybe this is not coming from their nuclear plant, maybe it's coming from one of their coal or natural gas plants. Similar idea, they're burning coal, they're burning natural gas to spin a big turbine, to drive electricity over here. I've got power lines going all over the city, eventually getting to here. Now that electricity runs through a filament, that electricity actually bumps into the filament atoms. All that bumping creates a lot of heat. This glows so hot, roughly the temperature of the surface of the sun, I'm not making that up, it gets so hot it glows. Now I've got that whole process from Dominion Power converted into light and heat right here, and it's a pretty bright light. That's converted into light and heat, and then again, this is one of my favorite things about living in the time we live in. We figured out, this is crazy, we figured out how to make motion out of light. That's insane. And so I can just take this stuff, it's just nice harmless light, same stuff we get from the sun all day, and I can convert that into electric potential and eventually into kinetic energy. So I can drive a car around with just this stuff. This stuff is massless, it goes the speed of light, and we're getting boatloads of it for free all day long. Yeah, all day, not night, but the planet itself is getting boatloads of this stuff all day long. So I just love that I can do that we figured that out. That's awesome. Because, first of all, it's just kind of fun to do. Feel kind of like magic doing that. But if the better we get at that, the better off we're going to be. Because this is free, not this stuff, but the sun stuff. That's free. It's coming all day long. It's going to be coming as long as we're around. So we've got a sun that we're going to be gone before it burns out. And so it's just free energy, free energy. So the whole fight over should we drill or coal or whatever, that stuff's free. It's good stuff. And then I have one other, speaking of free stuff, one other demonstration of that. If I went to here, I think. All day long, the sun is warming different parts of the earth. And when you might remember from like 8th grade or something that when you warm air, it expands. And so we've got these places all over the earth where there's less pressure and you've got expanding air, and that creates air kind of zooming around all over the planet. We call that wind. And we can use that wind to drive a turbine. And so, let's see, I've got a little light here. And it might be directional, it might be an LED. There it is, okay. So, I've got a little light here, and LEDs are nice and bright, and all I have to do is get some wind blowing past this thing, and I can turn my lights on. And again, that's free. The sun all day long is creating wind. I don't think we're ever going to run out of wind. And so here's another way to turn the lights on and do whatever you need to do. That's called doing work. So the sort of life lesson there is wind and solar is free. It's good stuff. The class lesson for the midterm is what you're witnessing is a transfer of energy. And that's another definition of work. Question? Good question. So the question is, what would I call wind before it's something more useful? I would call that, it's really well, there's a couple ways to think of it. You could think of it as thermal energy because it's coming from thermal differentials. So you've got a hot place and a cool place, or a pressure differential. And maybe more technically, it's kinetic energy. So when I've got wind, I have mass. Air molecules are heavy. So I've got mass bumping into my fan blades, into my windmill blades. And so I've got air molecules actually bumping and transferring energy in the collisions there, and then converting that into electric. That's a good question. So I want us to be, and the reason I've done this demo and several others is I want us to be thinking about that process of transferring energy. If you want to do anything on this planet, you need energy. You can't just make it for free. You have to convert it from something else. So I want to drive my car. I have to go get some energy somewhere and convert it into the kinetic energy of my car. So you can think of this windmill, or you can think of the motor in my car as just devices that we've made to convert energy. So the engine in my car is an energy conversion device. It takes gasoline and converts it into kinetic energy. So and that's called doing work. Work is that transfer of energy. So if I want to do work, such as go upstairs, drive somewhere, think, write something down, turn on the lights, operate my Wi-Fi, those things all require energy. I need work. I need to do work to do that. So if I want to send a text message, I need to do work. I need to take electric potential from the battery and convert that into cell signals or Wi-Fi signals. So I'm actually doing work. I'm converting energy from one type to another. Okay. Any questions? One other quick thing of review, then I think two other things, then we'll get started with some eye clickers in a minute. Worth knowing, I've mentioned this before, we physicists tend to categorize all these types of energy into mechanical and non-mechanical work. So in this class, a lot of what we're talking about is mechanical work. Walking upstairs, driving a car, lifting something up. That's all mechanical energy. So I've got gravitational potential energy. So anything that's above its 0 point, which is arbitrary, but anything that's above its 0 point, there's potential energy in that. I've just taken, let's take this gizmo. Right now it's got no energy. I'm going to call this 0. I'm going to come along, I'm going to do work. I just did force times distance, and I lifted that. I added energy to this. It's got no energy, now it has some. Where did it get it? I transferred energy to that by applying a force over a distance. That thing now has energy, and I can carry it around. It's like a little battery. I've got this energy that I did all this work, and now I can store. It's stored. It's in potential energy. That's another word for, that's why we call it potential energy. It's stored energy. I walk around all day with this. It's like a little battery. I've got energy in that. And then later, I can drop it and drive a nail, a teeny tiny nail. But we had a 22-pound weight up here the other day. I really drove a nail in. But similar idea. Somebody before class even started came along, and when we did that, the weight fell and drove that nail in. Somebody before class took that 22 pounds and did work on it, and now it had that energy. It was hanging by a string all for like the first 10 minutes of class. And then I went and I burnt that string, and then the potential energy was released, and we were able to do work. And so I think I've said this before. One way to understand the universe, and this is one of the utilities of the concept of energy, is we can largely understand the universe as just energy going to its lowest state, as energy finding a way down. And so somebody lifted that 22-pound weight up and then tied it to a string. It's sitting there as stored energy. Literally think of it as like a battery. And given the opportunity, it will lower its energy. So that string was just fighting against its potential. Then once I burnt the string, the weight was able to exhibit its potential and do work. So anytime I have taken, and I've said this before too, anytime I've taken two things that want to be together and separated them, that's called doing work. I've done work in doing that, and I can store that as potential. So our two examples up here are a planet and something else, or two ends of a spring. And if I take two ends of a spring, or even doesn't even have to be a spring, anything springy, if I bend it away from its lowest energy state, I can store energy in that. So winding up an old style wristwatch, you were doing work by twisting a spring, and then throughout the day that spring unwinds and lowers its potential and goes into the motion kinetic energy of the hands. I'm trying to think other ways we store spring energy. Yeah, like an old school catapult, you bend it back, that's doing work, and then you let it go. That's all I got. Okay. And then kinetic energy. We haven't even gotten into rotational, so we won't worry about that. But anytime something's moving, it has kinetic energy. So that's our types of mechanical energy. And then friction is usually the culprit for sapping mechanical energy out and turning that into heat. And so when you are driving down the street in your car and you hit the brakes, if you lightly hit the brakes, the brake pads rub against the brake rotor, and all your kinetic energy is being turned into super hot brake rotors. If you've ever driven around for a while and then stuck your finger on your brake rotor, it's crazy hot. If you watch like a race car, like a NASCAR event at night or something, their brake rotors are often glowing. They're so hot. Or if you slam on the brakes, there's not relative motion between your rotors and your brake pads anymore. You slam on the brakes, they're locked up. So they're not relative motion. And it's the tire against the road that is taking all your energy and converting it into heat. So you're going to melt. I don't know if you've ever walked outside and seen somebody laid rubber. They actually melted their tire by spinning like that, and they actually created so much heat. They were turning fossil fuels into heat and melted rubber. Yes? Yes. Great question. The question was about skidding and relative motion. I mentioned the other day, we were talking about, somebody asked about traction control. There's two types of kinetic energy. Two types of friction, sorry. Let's see if I have them up here. No, I don't. There's two types of friction, static friction and kinetic friction. It's worth knowing those are different, and kinetic friction is almost always less. You have traction control in your car, and you have anti-lock brakes in your car for that reason. So if I want to slow down rapidly, I do not want relative motion. I don't want slipping or sliding. And because what I want is static friction, which is greater than kinetic friction. So I want static friction. So if my car tire is rolling on the road, the surface of my tire and the road are not moving relative to one another. I'm just getting this nice rolling. There's no slipping or sliding. So even though my car is moving, the tire is not moving relative to the road at the point of contact. So I'm actually taking advantage of static friction. If I'm not slipping or sliding, I can accelerate faster and I can brake faster. If I don't have my analog brakes on and I slam on the brakes and I just start sliding down the road, I now have relative motion between the tire and the road. That's kinetic friction, which is usually way less than static. And I'm going to, just try, I don't know, maybe try it. Get up to some speed. A lot of cars have the turn anti-lock brakes off button. I don't know, try this in a safe with a helmet and a closed track. But turn the brakes off, get up to speed, hit the brakes, and you just skid to a stop. Then do the same experiment again with anti-lock brakes on, and you'll roll to a stop in like less than half the time. So it's the lesson there, kinetic friction is less than static. Okay. Almost time for some eye clickers. The only reason I wanted to throw some equations up, again, as I've said before, on the exam, I think the only number you should have in your head is 9.8 or 10. That's that acceleration due to gravity. But in terms of formulas, I don't think I'm ever going to ask you to crank out a number. I actually took this class on undergrad, and I found that really hard. I was really good at cranking out numbers, and so give me M, give me G, give me H. I can multiply them together and give you gravitational potential energy. But that's not why I'm giving these formulas. The reason I'm giving the formulas is just so you can see the relationships there. Question? Great question. The question was, what chapter should you read in the book? Definitely, everything we talk about is in the first 4 chapters. But there's a lot more in the first 4 chapters than we've talked about, because that's a lot of reading for 4 chapters. Maybe you could take these 10 things and look them up in the book and read the section on Newton's law and the section on power. I'll put that back up in a second. Quick, everybody take a picture. Okay. But I'll pull that back up in a second. I just wanted to say that the reason I'm giving you formulas is just so you can see the relationship. I want you to know that kinetic energy goes up with the square of velocity. I'm not going to ask you to calculate kinetic energy, but you should know that if you're driving down the road at 20 miles an hour, you have 4 times the energy that you had when you were going 10 miles an hour. If you hit a wall at 60 miles an hour, that's 4 times the energy if you hit the wall at 30 miles an hour. That's worth knowing. You should know that work is force applied over a distance. I'm not going to ask you to calculate force times distance, but work is force applied over a distance. You push on something over a distance, you're doing work. That's how work is usually done. Power is the rate of change of energy. There's the formula. I'm not going to ask you to calculate it, but just know it's the rate. Divide anything by time, you're now calculating a rate. And so if the example I used last night was, I had 2 cars, both go 0 to 60. They're both at rest. Sometime later, they're both going 60 miles an hour. They both increased their kinetic energy. The more powerful car was able to do that more quickly. So if one car goes 0 to 60 in 4 seconds, another car goes 0 to 60 in 10 seconds, both changed their kinetic energy the same amount. One was more powerful because it did more quickly. And then, hey, E equals mc squared. Taking a physics class, that's got to come up sometime. And the sun all day long is converting mass into energy. And you have this bonkers exchange rate of 3 times 10 to the 8th squared. So 9 times 10 to the 16th. And 9 with 16 zeros after it. Take 1 kilogram, you get 9 and 16 zeros joules of energy. It's crazy. Okay. Here's my 10 things that I was thinking about when I was writing the midterm, and I have an eye clicker for each one. So we should probably get going on the eye clickers. You good? Okay. Those are my top 10 concepts worth knowing. have an eye clicker for each one, starting with this one. Ready, go. And since we have 10 of these, and we have 20 minutes, do the math. Let's spend 40 seconds answering each one so we have time to talk about it. And for the sake of anyone that's going to watch the video, I'll say the question. The question is, what holds the grass in place when you're cutting the grass with a lawnmower? The roots, air resistance, vacuum, or inertia? Smart. All right. 5 more seconds. Okay, your lawnmower does create a vacuum. That's how it gets the stuff into the bag. And you'd think it would be the roots, but actually you could probably cut grass if there was floating in space or something like it. So it's actually the inertia of the blades of the grass itself. It's the inertia. If I was a little more brave, the demonstration I would do, which I did once, and I feel like I was pushing my luck. I had a nice, like a big blade. I threw up a banana or an apple or something. I sliced it, and it's a nice demonstration because you can slice something in the air. You know, Fruit Ninja. You can just throw something up, and if you do it right, the apple is falling through the air, and the blade just passes right through the apple. And you'd think there's a blade pushing against the apple would go flying across the room, but the apple has inertia. It doesn't want to change its state of velocity. It's falling down. It wants to stay doing that. Grass, when you're cutting, is just sitting there. It wants to stay sitting there. So you take a blade sharp enough, it'll pass right through the grass, and the inertia itself will hold the grass in place as you cut through it. So all that just to say, something at rest wants to stay that way, and you can take advantage of that. Okay. Number 2. Ready, go. I've got an airplane going at constant speed. That's your hint. At a constant altitude. Which one is true? Thrust equals drag, lift equals weight. There's no force, there's no net force, or all the above. Okay, let's take 10 more seconds. Answer is all of the above. And again, here's your hint. Something going a constant speed in a straight line is not accelerating. So maybe another way to say this, the definition of acceleration is change of velocity. There's 3 ways I can change my velocity. I can speed up, I can slow down, I can take a left. All of those constitute accelerating. If you accelerate, you need a force. So if there's no net force on you, you're not accelerating, you're continuing in a straight line. And A and B are just another way to say no net force. Question? Good question. The question was, does the word overcome? Yeah? That? Okay. Yeah, I can see that. Overcome means like maybe thrust is more than drag. Yeah, I'll give you that. That's not what I was thinking. I was thinking you've got this drag, your thrust just needs to equal it, overcome it. That's good. That's tricky. Yes. Speeding up, slowing down. So that, a change of velocity, in other words, an acceleration would be speeding up, slowing down, or turning, changing direction. So I need if I'm driving down the road, I need a force if I want to speed up, slow down, or even steer. I need forces for all those. Yes? That's an acceleration. We haven't gotten too much into the definition of a vector, maybe not at all in this class, but velocity is directional. And so walking this way is different than walking this way. And so if I go from walking that way to walking that way, I accelerated. There was one more question? Yep. Yeah, I think I could have used a better term than overcome. I think I should have said equals. Yeah. Yeah, so forget I said overcome. Yeah, I think you're right. What I was trying to say in part A was, you've got this wind resistance. Something needs to cancel that out. Okay. Number 3. Got an astronaut floating next to a big spaceship. They're both stationary. The astronaut gives the spaceship a big shove. What happens? Ship doesn't move. They have equal and opposite accelerations, or they experience equal and opposite forces, or the shove is overcome by the gravitational force. Five more seconds. Okay. Depending on your thinking, you might think that it's a big spaceship, so it's anchored, it's not going to move. Nope, there's nothing anchoring it other than its own mass, and that mass is not infinite, so it's not rigidly anchored. Or you might think they both just fly away because there's nothing anchoring them. Neither is true. Here's what is constant between the two, and they are both going to experience the same force, C. So that's Newton's third law. And as weird as it is to sometimes it's counterintuitive, you can't get away from that. You can't get, if I push on something, it's going to push back on me in equal and opposite. So I've got a little astronaut and a huge spaceship. The astronaut is the one doing the pushing. The spaceship's just sitting there minding its own business. Those two objects are going to experience equal and opposite forces. There's no way around that. The example I used like a couple weeks ago in class was, when you swat a fly, I know it's weird to think about it, that fly is pushing on you the same you're pushing on the fly. You're pushing on each other equal and opposite. The only difference is you're much more massive, so you're not the one probably doing the accelerating. Okay. So if you've ever like gone in to high-five someone and they just got really aggressive about it and your hand hurt, you guys were actually experiencing the same force. Same force. All high fives are mutual. Yes. Yeah. I just want to make sure that we're clear. What's gonna be equal in this situation? It's not accelerations. A is each going to accelerate the same. That would only be true if they had the same mass. So regardless of mass, they will both experience the same force. All right. Okay, we're gonna see if we can get through all these. Number 4. What's not true about gravity? There's no gravity in space. Gravitational force is mutually felt by the two masses. Gravitational force is always attractive. Gravitational force is really weak. Or gravitational force diminishes with distance. Remember, we're looking for not true. Five more seconds. Oh, good. Okay. I'm not an English major. Someone's going to probably tell me that I worded this wrong. Here's a common misnomer. There's gravity everywhere, including the most far reaches of space. If you were to look at Newton's fourth law, GMM over r squared, the only time that equation goes to 0 is at infinity. So if you took a completely empty universe, put one speck of sand in the middle of that universe, there's now gravity everywhere in the universe. the gravity due to you, and again, this is one of the things that's crazy about Newton's fourth law, the gravity due to you extends throughout the entire universe to infinity. Your presence creates a dent in space-time that is never zero. It never goes back to zero. And so there's gravity everywhere. And so we'll talk more about this, but anytime you see an astronaut floating around, they're not in zero G, they're just in free fall. Common misconception. So anyway, the answer here is, yeah, no gravity force. Yeah, hey, there's no gravity in space. That's not true. That's not true. Okay. Any questions? Okay. Oh, and just also to reiterate, as far as forces go, gravity is amazingly feeble. That formula, gmm over r squared, the g has an exponent like -11 or something. Gravity is extremely feeble, so it's rarely encountered until you have something like a planet or something. Okay. Moving on. Galileo dropped 2 balls from the Leaning Tower of Pisa. I think that's a true story, actually. Heavier ball fell twice as fast, heavier ball 4 times as fast. They were same rate, or small ball fell twice faster or 4 times as fast. Good. Yes. The big ball is twice as heavy. Good point. Yeah, you can't draw a quantitative. There we go. All right, 5, 4, 3, 2, 1. Mass doesn't matter. They all fell at the same rate. The answer is C. Okay. So the day I had that vacuum pump up here and you saw a feather fall like a rock, that was the whole point of that, is that everything without, is there something happening up there? Okay. Everything without any other forces acting on it are going to fall at the same rate. So the point of this question was, and Galileo chose 2 objects that don't have a lot of air resistance. Everything falls at the same rate. On this planet, everything speeds up at 9.8 meters per second every second. So if Galileo were to drop 2 balls in Italy, those 2 balls are going to be going 9.8 meters per second after 1 second. They're going to be going 19.6 after 2 seconds. They're going to be going 29.4 after 3 seconds, et cetera, et cetera. There's a question way back. In this question, on the midterm or anything, I would specify if air resistance was a factor or not. So I would say neglecting air resistance or something like that. Good question. So in this case, 2 like rocks or something from the Leaning Tower of Pisa, air resistance is not going to be much of a factor. Okay, yeah. So if 2 objects experiencing only their own weight, no other forces, they're going to fall at 9.8. And you can round to 10. So if you jump off a cliff, you're going 10, then 20, then 30, then 40, then 50 meters per second as you descend. Okay. 5 to go. We'll see if we can get through them. Ready to go. I'm riding my bike. Slam on the brakes. A, my acceleration is backwards. B, the road is slowing me down. C, I shouldn't slam on my brakes because kinetic friction is less than static. Or D, all the above. Okay. Five seconds. Okay, the answer here is all the above. You can be going that way and accelerating that way. All that means is you're slowing down. So I'm going down the street, I'm going this way. I start accelerating this way. That just means I'm slowing down. And then if I come to a stop, I've decelerated all the way to zero velocity. I could then accelerate this way and go backwards. That would be weird, so I'm not going to do that. So, but while I'm slowing down, I'm accelerating backwards. Who's pushing me? I can't push myself. The only thing I'm touching is the road. So the thing doing the accelerating on me or the pushing me is the only thing I'm touching. It's the road. And I should gently squeeze my brakes. Otherwise I'll skid out, and I don't want to use kinetic friction because kinetic friction is way less. Question? Yeah, my volt. The question was about friction. Kinetic friction is the friction of sliding. So if I'm riding my bike down the road and I slowly come to a stop, I use static friction to do that. I use static friction to do that because my tires were never sliding. If I'm riding down the road and I lock up my brakes and I start skidding, that's kinetic friction because my tires are sliding along the road, not rolling along the road. And unless you're drifting or something, you want the static one. Question? Is kinetic friction always less? I think I remember reading about some really weird situation where it wasn't. But let's just assume always. Yeah. Yes? Yeah. Yeah, so that's a good question about who is slowing you down. And I think here's a good way to think of it, is I think what you're watching go down the road is a me bike system. There's me and a bike. We're all going the same speed. In order for that me bike system to change speeds, like slow down, something external to the me bike system has to push on it. And so, and this is a neat thing about physics, is that you could drive your minivan off a cliff, and inside the minivan, you could be fighting and punching and playing basketball, whatever you're doing inside the minivan. None of those things matter. The minivan system is going to accelerate at 9.8, regardless of what's happening internally. So internally to the me bike system, I've got tires and brakes, and I'm squeezing my handlebars, and I'm stepping on the pedals. All those things are internal to the system. Okay, let's do one more. We might have to call it a day. Let's see which is my favorite one. We should probably, let's see. Let's just do the next one. Okay. Let's do two more real quick. Ready? Quick. I'm going to give everyone 15 seconds to buzz in, and we're just going to do two more, then we'll call it a day. 5, 4, 3, 2. Don't even look at those plots. I'm just asking you, what is the slope of your velocity plot? Position, velocity, acceleration, or force? Yes, people got it. It's acceleration. Acceleration is the rate of change of velocity. Another word for rate of change is slope. Let's do, let's do this one, then we're done. Okay. What's not true? Bowling ball converts potential energy into kinetic. Baseball player sliding into home is using friction to convert his kinetic energy into heat. There's no such thing as negative work. That one's wrong. You can do negative work. Negative work just means taking energy out of the system. All right. Let's call it a day. Yeah, C's wrong. Negative work is just taking energy out of a system. See you Friday.